Welcome to homework.
So here we're essentially finding 3 de Broglie's wavelength, and we can say that for part A, we're going to be using table 37, 3. And we can say that here, lambda, the wavelength, would be equal to h, Planck's constant, over the momentum p. This would be equal to h over the square root of 2 times the mass of the electron times the kinetic energy. This would be equal to hc, Planck's constant divided by, or rather, Planck's constant multiplied by the speed of light divided by the square root of 2 times m sub e c squared times k. So we're essentially multiplying this by c over c. We're allowed to do that because that essentially just equals 1. So then the wavelength here would be equal to 1,240 electron volt nanometers, and then divided by the square root of 2 times the mass of the mass of the electron sub e times c squared. So here the energy of 511,000 electron volts multiplied by the kinetic energy of 1,000 electron volts. And we find that the wavelength here is 0.0388 nanometers. For part B, we know that a photon's de Broglie wavelength is equal to its familiar wave relationship value. So we can say that lambda here would be equal to hc over the energy, and this would be equal to 1,240 electron volts nanometers. This would be divided by 1.00 kilo electron volts, and this is equaling 1.24 nanometers. And then finally, for part C, the neutron mass may be found in Appendix B, and then we're simply using that mass in order to find the wavelength. We're also going to be using the conversion from electron volts to joules. So now we have that the de Broglie wavelength is going to be equal to the Planck's constant divided by the square root of 2 times the mass of a neutron, or we can simply say lowercase n, times the kinetic energy. And so this would be equal to the square root of 2 times the mass of the neutron, 1.675 times 10 to the negative 27th kilograms, and then multiplied by 1.6 times 10 to the negative 16th joules. And then for the numerator, Planck's constant, 6.63 times 10 to the negative 34th joules second. And we find that the de Broglie wavelength would be 9.06 times 10 to the negative 13th meters. This is your answer for part C, your answer for part B, and again, your answer for part A. That is the end of the solution. Thank you for watching.